Here we go. Okay, welcome back everyone. And let me show you a little bit what I did in our studio, looking at this global melt. First, all right, so I'm labeling this session as global warming correlations. And I'm studying, is that large enough or is that too small? Let me try, is this going to work? Yeah.
The only thing we can do is this part.
Which one?
It's just this. That's the only thing. It doesn't.
Oh, that was spread it horizontally.
Yeah, that's the only thing we can do.
But the size of the text is the same.
It doesn't get bigger.
No?
No.
Okay, let me. Okay.
That was a little bigger. It's still small.
Can you hear me, Father?
Yeah. Okay, that doesn't work, and this doesn't work either. I'm sorry, it's not that large. But if you want to sit forward a little bit, anyway, I'm recording this, so you'll have it, all right, as an example. If you want to come a little closer, it's fine, all right, you're welcome to sit up closer. So I'm studying the possible correlation between human population growth and several other variables. Give me a minute, someone is on chat here. Who is on chat? Is enough big to see it? Who is this? I don't know who's chatting this. Have them pick up Zoom. I can see it on the computer. Okay. How do you know it's Gloria? Does it say anywhere?
I can't read it either.
I see Gloria.
Where?
In the blue letters. She said it's.
Oh, here. Okay, I see.
Oh my gosh.
And Ed too. Okay, thank you. Yeah. All right. Very good. Thank you. Yes, you're the youngest one in the group. Very good. Thank you. So I have 5 variables. All right, and the fixed variable. No, the independent variable is human population growth. And I want to see, then I'm looking at CO2, temperature, ice, and sea level as the dependent variables, possibly dependent, to see if there is really a correlation between human population growth and CO2 increase, and then between CO2 increase and temperature increase, then between temperature increase and ice melt, and then between ice melt and sea level rise.
And these are all continuous variables, right?
Yes, they're all continuous variables. So it spans the last 4 decades approximately, all right? So just under half a century. And the data is in my Bio 600 folder together with this session of our studio, which we're calling MAT project, MAT_project. Oh, at this point, I also have to say that this is, I did this, yes, but this I did jointly with the professor, Dr. Sanchez. Okay, so exactly, I'll tell you up front, I was the one who came up with the ideas, and he came up with the technique. All right, so all the programming, before I get in trouble, I want to give credit to Dr. Sanchez. He was my techie. All right, so I came up with the data, and he came up with the coding. So it's collaborative. It's collaborative. Okay, there's another tab here I'll show you because I was able to upload the data also into our studio through the console. And yep. Exactly. So these are different sources, right? Here is just a rundown, chronological by starting in 1978 and ending in 2016, last year. All right, so here's showing 22 out of the 39 events or entries. So each column is a variable, starting with human population growth, which is going to be my independent variable. Why? Because population growth is not dependent on CO2 or the temperature or ice belt or sea level rise yet, right? Okay, but the others, so the question is, are these other variables dependent on population growth or not? Okay, so there's the growth rate here, starting in 78, just a little over 4 billion, to 2016, a little over 7 billion, so it's almost doubling in 40 years, almost doubling the population of the world in under a century. If we go to the century, it will be more than double in half a century.
Is taking newborns, or?
Yes, this is population growth. So
Yeah.
it's a net.
Yes.
You know,
Yeah,
every
but-
year you take birth and death, and you come up with a number for every year. That's the net.
So we are reading more.
Yes, sure.
Right, we are.
Yeah, that's exactly right. Yes. That's one factor, right? But also, we are, as a species, we are in the log phase of growth. Remember the sigmoid growth curve, right? Well, we are in the log phase, right? Which is exponential. It's a geometric growth. 1, 2, 4, 8, 16, 32, 64 is a geometric growth. It's not arithmetic, right? So we're in that phase. And the big question, of course, what is the carrying capacity of the world, of Earth, for the human species? Because we can figure out the carrying capacity for other species, essentially when the resources start to when that other species, whatever that species is, starts to deplete the resources, the natural resources, then it starts to balance out, right? And it comes to a steady state, unless the climate changes drastically, that state will be maintained, and you get a stable community, all right? But for the human species, we don't know what is the carrying capacity of Earth, because we produce our own food. No other animal actually produces their own food. Well, plants do, but then animals feed on that. Okay. But we also have this other issue of artifacts that we create, artificiality that keeps us alive better, longer. So these are the issues. Okay, anyway, just tying it to the potential of the possibility of global warming, and what is, because it's actually one of the chapters is of Laudato Si, the Pope's encyclical on the environment, right? Has 6 chapters. Chapter 3 is precisely the human aspect, the human contribution to global warming or to climate change, that whole chapter, all right? Okay, so then CO2 increase in parts per million. I'll just tell you briefly the units here. Parts per million. Temperature rise in degrees centigrade. Obviously, it's a fraction of a degree, all right? Excuse me. Then the Arctic ice melt is measured in millions of kilometers square from the surface down. Okay, so they're looking at surface melt in millions of kilometers square. And then the sea level rise is actually measured in millimeters per year. Millimeters per year. Okay, interesting. All right. So that's the data. Let me go back, if I can find it, the project here. Okay. The first thing we had to do then is to retrieve that data set, which I have labeled as Cioffi.csv, so it's a CSV file, right? And load it into mat_project And then we had to reassign the column names because they were too complicated. And so we just gave it simple names to the columns. A simple short name, year, pop, CO2, temp, ice, and C. All right, has no units or parentheses or anything like that because that confuses it makes it too complicated. So the first question is, how tight is the data to their own regression line? So how tight is the data? Is there indeed a trend or not for those 5 variables? Dr. Sanchez showed me how to do a matrix of the plots so that it shows in a single output. This is what is known as a matrix. This is a 2x3 matrix with the 6th position, 2, 3 actually empty. All right. So in the matrix, this is 2 rows by 3 columns. And this is the coding for it. If you want to show it all in a single vision like that. Here. PAR, MF row, and here's a concatenation. This describes a matrix of 2 rows and 3 columns. Okay? Then everything that is underneath, and it's in the same chunk. So you see the chunk starts here, all right? So this is the first command, the first argument of the chunk, and then each one, I'm asking the plot of each one, everything against the year. So the x-axis is the year, and then the y-axis is going to be each one of the variables. Follow? X-axis, so we got population versus year, we got CO2 versus year, temperature versus year, ice versus year, and sea level versus year, right? That's the first line. The second line is the linear model, in other words, to give me the regression line. And then we can see visually how tightly those 5 variables are to the regression line, to the trend, right? So these are all linear trends. Year, of course, is perfectly aligned because it's just sequential, it's a sequential numbering. And CO2 is also very tightly aligned to the mean, to the regression. Now we, excuse me, we start getting more scatter with temperature, okay? Because this is affected by what? Season, right? The temperature is going to be seasonal. So this scatter, see that it's not as tight around the mean that is CO2, for example, right? Because CO2 is a very long-term cycle. But weather is on a yearly basis. So we can assume that the scatter here, I mean, it's reasonable to assume that the scatter is because of seasonal summer, winter. Thank you very much. Okay, ice melt. Also, some scatter. Why? Again, seasonal, right? The maximum and the minimum. Remember the graphic display of 20 years of the Arctic photographs. I was expanding and contracting, all right? It has a rhythmic. So, and that's a reasonable explanation for the scatter on this plot. But you notice, what's the slope? Is it positive or negative? Negative. Right. So this is trending melt. All right, melt. So in other words, less ice in 2010 than in 1980. Straightforward. Sea level, again, rise, but some scatter, not as scattered as temperature or ice, meaning that it's less influenced by season. In other words, there's a delay, there's a lag between the time that the ice melts seasonably and the actual spread of that liquid water now to raise the level of the ocean globally, right? There's a lag there. So that smooths out, if you will, the seasonal effect, okay? And so that's why it's logical. In other words, this is my opinion, this is my interpretation of why there is less scatter on the sea rise than there is, for example, with temperature. All right, this one is more subject to, temperature is more subject to seasonal change than the sea level rise. But there is some scatter there. All right, moving forward then to do the basic stats, summary stats for each one of these. We're going to glean different information from each one, from the year basically. I mean, who cares what the mean is between 1978 and 2016 for the purposes of this data, right? Of this analysis. But what I get from the basic stats of the year is simply the start and the end, right? So that's translated as minimum and maximum numbers on those stats. So it's more or less 4 decades, like I mentioned, just under half a century. Population, I don't make any sense out of this data. I don't know what it means. Okay, but, anyway, it's there just for consistency because I ran the stats of the whole thing, of the project as a whole, right? All 5 variables. CO2 is significant again because it gives us a starting value of 334, almost 335 parts per million, to a little over 400 parts per million. All right, so that's an increase in the 40 years, in the 4 decades. That's a net increase of CO2 of almost 70 parts per million in those 40 years, net increase. And steady, because you can see that each number here is increasing, right? From the first quarter to the third quarter through the mean, it's always increasing, sorry. Temperature the same, starting temperature and ending temperature. It's an increase of almost 1 degree centigrade, just under 1 degree centigrade in 40 years. Net rise globally. Ice is, if you want by the numbers, the most dramatic number, almost 3 million kilometers square of ice melt in 40 years. So just under, if you want to figure out a rate, just under 1 million kilometers per decade. But finally, at the end of the day, the sea level rise, okay, is under 2 millimeters in those 40 years. 2 millimeters, okay? 2 millimeters. So at the end of the day, yeah, all that dramatic melt and dramatic increase of CO2, all right, comes down to just under 2 millimeters in 40 years. In 4 decades, exactly. So where's the beef, right? What's the hype about? Here's a little ruler. I know the photo is, I don't think the camera is working on this thing, but there's a little ruler. Let's pass it around for a moment. This is 15 centimeters, right? 15 centimeters. So you can find 2 millimeters there. It's definitely under 1 centimeter, right? It's 1/5 of a centimeter, right? Yes, oh, sorry, it's a combination between NASA, NOAA, and I don't know what I use for the world population, but some kind of a agency that counts the numbers, but mostly NOAA and NASA are the sources. So they're measuring this very accurately with satellite and so forth. However, if we extrapolate a little bit, let's keep it, for simplicity's sake, let's keep it at, well, let's say this is 40 years. So let's just extrapolate up a little bit to 50 years, make it half a century, 2 millimeters. 2 millimeters in half a century, so that we can do an increase, all right? In 1 century, it will be 4 millimeters, right? 1 century, 2 centuries, 8 millimeters. 3 centuries, 16 millimeters. What are we at, 2 centuries?
2 centuries?
2 centuries, 60, so 1.5 centimeter, all right? So 1 millennium would be 1 decimeter, 10,000 years, 1 meter. 1 meter in 10,000 years.
10,000 years.
Yes, but that's if it's linear. That's if it's linear.
If it doesn't stop.
In the span that, so the linear model fits okay. We just saw the graphs, okay. The linear model fits okay because we're looking at 40 years. But if we look at a larger span, maybe a better fit would be a curve, would be a log instead of a linear phase. And a log phase is no longer arithmetic, but a geometric progression. Okay, so arithmetic progression, linear implies that it's an arithmetic progression. 1, 2, 3, 4, 5. All right, but a geometric progression, again, is a doubling at each iteration. So 1, 2, 4, 8, 16, 32. Pretty soon, when you get down to the 8th or 10th iteration, you're already in the thousands. And then the thousands are going to become hundreds of thousands, and those hundreds of thousands are going to become millions. All right, so it's very fast uptick. And that's why if the rate is nonlinear but geometric, the rate of increase, then that's a concern.
Yes, in 10,000 years, we probably have the technology to sink CO2 or to control the temperature.
That's the hope and that's the expectation.
Which
Exactly.
is gonna change again,
Yes. But again, we were only looking at, this is this is extremely simplistic because first of all, I'm only looking at CO2, all right? We also have to add methane here, for example, and the cumulative fact that as the ice is melting, and Tony pointed this out, CO2 is released, that is sunk, that is trapped, and methane is also released. So it compounds, it accelerates this graph also. It can send it into also a geometric, a logarithmic increase, all right? So those are the issues there. That's why I'm saying this model is extremely simplistic. But anyway, it's a start. And what I wanted to see at the end of the day is if there was a correlation, since it's the last thing we covered in class, between each one of these sets, all right, pairing them up one by one.
That is the p-value.
Well, okay, so I also ran the, so I'm going to get p-values now with correlation here. So here we go, starting with the first correlation. Excuse me, is population and CO2. In other words, the increase in CO2 as related to population, okay? 99.9967, all right? That's very close to 1. So, which is an absolute correlation. And look at the p-value. You got 16 zeros here, a decimal point and 16 zeros. All right, so that's extremely significant correlation there between just population growth and CO2 increase. That's the first one.
Yeah.
All right. Moving forward then, I think I can do 2 at a time on the screen. Now CO2 to temperature. 0.912, still highly correlated, right? Highly correlated. Keep in mind that 1 is an absolute correlation, all right, absolute identity. So not as tightly as population and CO2, all right, which had a 99.6, now 91.2, but still anything in the 90s is extremely significant. And the p-value is again down to 16 zeros, so extremely significant there, right? Next correlation is temperature with ice here. Now is 0.902, so slightly less, but still very significant. Now it's only 15 zeros instead of 16, but still extremely significant and extremely strong correlation. Finally, ice with sea level rise, okay? 0.895, which is still considered very strong correlation. The p-value is down to minus 12 zeros, but it's still extremely significant, okay? So, I mean, these numbers really are not statistically significantly different from each other. They're way into the high correlation. The only thing to point out is that this one, ice melt and sea rise, is a negative correlation. It's an inverse correlation. It's still very strongly correlated. I went ahead and did the linear models also just to get a t-value. This one, okay, so starting with CO2 versus population. Again, the t-values are here. You can see they're both highly significant with 3 asterisks. Then the plot. Now this is a different plot, right? Because this is plotting CO2 versus population, how tightly it is around the mean. And you can see, indeed, there's a period here that sloped slightly lower. A trend is lower, but the average is very tight. This is CO2 versus population. The next one would be temperature versus CO2. Very significant correlation. I'm sorry, t-value. And the plot, a little more scattered. We saw that just with the temperature, this is because temperature is seasonal, CO2 is less seasonal, or I should say seasonal at a larger scale. Next one is, oops, sorry. Here, ice versus temperature. Again, highly significant correlation. And the slope now is negative, right? So it's an inverse relation. And the scatter is getting a little larger because now you got 2 things that are seasonal going on, right? The ice and the temperature are going to cycle yearly. Finally, sea level versus ice, still highly significant in correlation. And again, an inverse relation. As the sea melts, the ice, as the ice melts, the sea rises. right? So as there is less ice, there is more liquid water, more ocean. So that's why the relation is inverse. And again, the scatter, in my interpretation, due to seasonal change. Moving forward from here, what I'd like to do is add history to the columns. In other words, go back into historical time, possibly into the thousands of years, right? To see how it was trending, how there was a cycling that averaged out to a horizontal line, right? And now in this half century, how is getting off that flat line or no change to a significant change. And also add more columns. I want to add especially biodiversity loss and extinction rates, which according to the scientists are also increasing exponentially now above the background. So that's for the future, and then run the statistical analysis on the expanded data. All right, but it's the beginning of something that could be expanded into a project, and maybe even later, if I'm able to develop a PhD program, this could be possibly a project, one or more projects for a PhD dissertation.
Yes, because we know the CO2 increase with the increase of the population.
Mm-hmm.
But there are two types of CO2.
Yes.
Production, which is the CO2 produced by the human itself.
Yes.
Because of the cellular respiration.
Right.
And
Which
the
we can
CO2
consider natural.
produced
Yes.
because more people, more technology, more industry, more cars, more everything.
Yes, we can call that, let's call that the artificial. So there's a natural production and an artificial production. Yes. Mm-hmm.
So I was reading here, only 1% of the land mass is occupied by humans. I mean, it's very little, I think, compared with how much of the CO2, and we know we have 4 gigatons.
Right.
Excess.
Right. On a yearly basis, that's increasing, that's accumulating, that it's not being sunk or cycled.
Exactly. So
yeah.
We also need to correlate to see the excess of the 4, the one is causing the warming, global warming.
Yes.
If why, for example, most of that we have is natural lungs, you know, of the wilderness. I mean, something.
Right. The 2 main lungs, Amazon and the Congo Basin.
So, right. I mean, there are so many variables that we can play with.
Yes. Yes, they are.
I'm hitting to the point of it's not because of the human itself. I mean, the control of metabolism,
right.
Control of this stuff. It's more control what the human are doing.
Yes, exactly.
In terms of technology, in terms of using the
exactly.
In terms of what we're doing to live. I mean,
exactly.
The fact that we need to modify.
Yes. So in other words, yes. Okay. So first, I wanted to point out one little clarification and then a comment, because you mentioned that from someone is reporting that we only take up about 1% of the available land.
Yeah.
Well, but at what population density? It depends. Of course, if we put all humans shoulder to shoulder, it's going to be a very reduced area, but that's an extremely high density. And that's not a realistic density either, because we don't live shoulder to shoulder, you know, the whole population, the 7 billion. And so whenever I hear a statistic like that, that we only cover the whole population of the world, the 7 billion that we are, that we only take up 1% or 1% of the landmass, I ask, well, by what statistic and what kind of landmass? Because is it the available landmass? It's estimated of the landmass that we have of all the continents and the islands and so forth. It's estimated roughly between 1/3, only about 1/3 to 1/2 is inhabitable right now. So about half of the landmass that is not covered by oceans or lakes or anything is not available, mostly in the northern hemisphere swath because of permafrost and extreme cold weather, right? If we fast forward the argument of global warming, little by little, those land masses become more available. So whereas the sea level may rise and take in some coastland, yes, but proportionally, there's also land mass up north in the northern swath, which is where currently most of the land mass is between, let's say, what is today Canada, Greenland, and Siberia, all right? That is inhospitable right now, gradually becomes a little more and more available, okay? So what's the net gain or loss? The coastlands. The challenge, of course, is that I don't know exactly the number, but a significant percentage of the world population lives along the coast. So they would be most affected. However, they can also migrate inland, and this is such a gradual thing. You're talking about 2 millimeters per 2 millimeters every 40 years. Okay, so that's, for now, that's very manageable. But again, it's not the same, that's uniform, it's not uniform. The model is much more complex, the reality is much more complex, right? In some areas, it's more drastic, like for example, it really struck me, because I didn't know that when, if Greenland melts, that the sea will recede by several thousand kilometers around Greenland. That's extremely significant, and that's from water, from ocean water that's being held in the North Atlantic, close to the land. That's dramatic. Okay. So, yeah.
And there's two things also that affect, like, for example, sea level rise.
Mm-hmm.
One of them is coastal morphology.
Yes.
Coastal morphology here in Miami Beach, everybody says, oh, look at Miami Beach, you know, the climate change, et cetera, the flooding. The problem is that the way that the coast is in Miami Beach is totally different. The angle is totally different. So the water tends to roll in Miami Beach. And in Fort Lauderdale, it literally like this.
It's more inclined.
And it doesn't, and it's because of the morphology.
Right. Yeah.
And the fact that the temperature is increasing because of, you know, maybe CO2, you know, the additional trapping gases. In the ocean, which we covered this when we went over water, hydrologically, as the water gets hot, getting hotter in the water.
Warmer, yes.
So it will tend to expand, so it's like a big bubble, and that increases the volume, and of course that's where you get some of that flooding with, and then you have the supermoons and all. So like you said, it's not easy. It's not a simple.
That's right.
You know.
That's right.
And unfortunately, some of the scientific community is also to blame for the skepticism, because you have some scientists that use incorrect data just to prove their point.
Right.
With the statistics,
right.
And they got caught.
Yes.
And that just sends that ripple effect of disbelief.
Right. Yes. I've always maintained that we live in two worlds simultaneously. There's the world of reality and there's a perception of reality, which is not necessarily the same. Okay. And so a lot of the education has to go into trying to bridge the gap between the perception and the reality. But keep in mind that these are long-term trends. And that's why the danger is that it's similar to these, I make a simple analogy again, just in my mind, these super tankers that are in the ocean that are huge, and I don't know how many kilotons of fuel, whatever it is, or you see them stacked with these containers, 4 or 5 stories high of containers. How can that thing float, right? Well, it's displacing its volume, but whatever. That ship is moving in one direction, say in open waters in the middle of the ocean at X knots. If that captain turns that engine in reverse, turns the turbine or the helix, la hélice. The propellers.
The
Turns the
propeller-
propeller in reverse, okay? It will be miles before that supertanker slows down or stops or reverses. Miles and miles, because there's an inertia. And that's what we need to be careful with, that
And
inertia.
you're absolutely right, because that inertia actually is a step reaction
Mm-hmm,
with temperature. And the step reaction is like, it'll get hotter on the coasts.
mm-hmm,
So a 2-degree increase on the coasts
mm-hmm.
actually will translate to an almost 11-degree increase in the middle states.
Look at that.
So
Okay.
you-
Because it's changing the climate above the ocean also.
Right, so
Yeah.
it's a very increase, because, 2 degrees, well, we complain about the humidity.
Mm-hmm,
If you're in Colorado,
mm-hmm.
you feel it.
Right, right.
You know?
Yes, it's not even. It's a very dynamic system. And that's also one of the things that I was trying to point out in the spheres that we saw, the hydrosphere, the atmosphere, and even the lithosphere, how it's dynamic systems, right? Some of it is short-term, but the more drastic one is long-term. And that's what we need to be careful, to the point of the actual continents moving around. That's pretty drastic. And Ed is commenting here, I don't know if you can actually read it, but the salinity of the ocean also has to be taken into account, because that can affect, the salinity is also affected by the acidification of the ocean, all right, by the extra mix of CO2. And also temperature can affect that. So yes, let me do something. Let me switch gears again, because that's the end of our studio that I have. Let me get out of that torture. All right. And hopefully it may be useful to somebody in their project from now to Thursday. But let me, so I'm going to stop this share and go back to the other share. Okay, folks that can hear me. I'm gonna stop this and
Yes, it is.
but I'm gonna send you another link in a minute. Let me close this now.